it occurred to me at that time that it's nice in the holiday season to say something about trees. They're endlessly fascinating to computer scientists, especially, and so as far as I know, I'll probably never run out of interesting things to say about them. This is the 6th annual Christmas tree lecture, and today I'm talking about something which is one of the most fundamental problems in coding theory. It's the question of how to get the best possible alphabetic prefix codes. And I'll talk a little bit about that. The main method I'm going to be talking about today is called the Garcia-Wachs algorithm, and I guess one way to introduce it is to show you the home pages of Garcia and Wachs. So Adriano Garcia was one of my, oops, I forgot to copy his CV. I clicked on this too. Anyway, he was one of my professors at Caltech when I was a student there. He's 70 years old this year and still very healthy, as you can see in the picture here. Very charismatic guy. Been a professor at UCSD for more than 30 years. And then one of his students, who's also listed, if you go to his CV, it lists all his students, and you can click on Michelle's homepage. And Michelle Wachs is a professor in Miami, and she is well known now for very deep research in areas of algebraic combinatorics, kind of like lattice theory, such as I was talking about last year when I was talking about lattices of trees. One thing you'll notice about her homepage is that she has a tree on it. In fact, this tree also would define a prefix code, and that's what I'm going to be lecturing about. So she must still be interested in trees. This was her thesis work in 1977 or 1976, 77, sort of like that, and it's still the best algorithm for this problem that anybody knows. When you have a binary tree like this, you can imagine that. Well, I'm actually going to take the case where the nodes that have no descendants, I'll draw them as squares, and circles will be nodes that have 2 descendants in a binary tree. And if you start at the root and you write down a 0 every time you go to the left and a 1 every time you go to the right, this would be 0, 0, 0. And here would be 0, 0, 1, and here's 0, 1, 1, 0, 1, 1. These symbols form a prefix code in the sense that if I take any string of zeros and ones whatsoever, just write down any random string of zeros and one, I could consider that to be a message on a 5-letter alphabet, because there's 5 leaves in this tree, and so almost any sequence of zeros and ones, maybe a random number generator. But you see, you go until you get to a leaf, and that gives you your first word of the code. Then 1, 0 is a code word. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1. Not a very good random number generator here. No, okay. Anyway, I'll show you another prefix code later. But the point is, if you have a prefix code, you can represent it as a binary tree, and if you have a binary tree, it defines a prefix code. So they're equivalent concepts, and that's the connection with trees today, is the idea. But it's also alphabetic prefix code, and that means that if I consider that these were like A, B, C, D, E, and I had a message, and I had a word made out of A, B, C, and D, and E, and then I convert it into binary like this. If one word is less than another lexicographically, like in a dictionary, then also in the binary sequence it'll be less than the other. So this encoding not only gives us letters, but it also preserves the order of words, and that's why it's called an alphabetic encoding. It depends on the order. Now the case of coding without an alphabetic constraint is main idea is, in that case, called Huffman coding. I think most of you know about Huffman coding. This is, suppose I have an alphabet and I know the probability of each letter in the alphabet. For example, you might say well, like A, B, C, say E is the most common letter, for example. And so we have weights, and I typically will say W0, W1, and in this talk I'm going to go up to Wn. There'll be n plus 1 weights on a if you have an n plus 1 letter alphabet. It turns out to be convenient to number it this way. And the idea for a Huffman code is to find a prefix code where we attach the W's to the leaves of the tree. W1, W3 might appear here, and somehow these things are hooked together in a tree. W2, but they don't have to be in left to right. They don't have to be in left to right order. The leaves don't have to be in left to right order. But the idea is that if the weights represent the frequencies of using these leaves, then letter K, let's say, has frequency or weight WK. Then the code for K has length LK, where the length is the depth in the tree. So, for example, this code has length 3, so we had to go down 1, 2, 3. This is depth 0, 1, 2, 3. So the cost of a tree, or cost of a prefix code, which I'm going to call a tree, is equal to the sum of the weights times the lengths. So what we try to find is a code that has the minimum cost. It'll require the fewest bits to transmit letters if the letters occur in that frequency. You with me on that? Now, it was one of the most basic things in information theory when Claude Shannon published his original work in the late 40s was to show how you could how entropy was a lower bound on the cost of a tree, and how you could get very close to the entropy by certain construction. And Dave Huffman was a student at MIT in those days, and he showed one of his teachers. He had this construction. He said that I can, Shannon showed how you can get close to an optimum code. I can prove how you can get actually the best possible code with given weights. And his teacher said, no, your method is too simple. It couldn't possibly work, because otherwise Shannon would have found it or something. I don't know. But it turned out that Huffman was right, and his paper was published, I don't know, 51 or something, very early. And I suppose a lot of you know him. He's a professor at UC Santa Cruz for the last 30 years or so. So Huffman's idea is this: suppose that the weights are ordered without loss of generality. Since the order of the letters doesn't matter, we might as well assume that they're ordered with the smallest. We know what the smallest weights are. His idea was simply this: you take the two smallest ones and combine them into another superweight, which is the sum of the two. And so you have these two leaves here, and so now you have new weights. W0 bar, or W1 bar, let's say, is equal to W0 plus W1. W2 bar is W2, and Wn bar is Wn. So we've gone from n plus 1 weights now to n weights, where we just added together the two smallest weights. And his idea is now solve this smaller problem that has one fewer weight with the same method. Combine its two smallest guys and keep on going until you've got everything down to one tree, and that's your best possible tree. Now the reason that Huffman's algorithm works, well, there's lots of neat, fast ways to implement it, but the reason that it works is not too hard to see. But I got a cheat sheet here so I can make it. I'll tell you the most elegant way to show it. Anyway, okay. So in other words, why does Huffman's construction work? So what we do is we take any. What I want to show is then that the optimum tree for given n+1 weights is equal to, or can be found. One way to find an optimum tree for these n+1 weights is to form these n weights, combine the two smallest, and then find the optimum tree for that, and then take this weight and expand it back again. So the proof that this works is the following. Suppose we take the cost of the optimum tree for the small number of weights, the W bars, and I add W0 plus W1 to it. This will be the cost of some tree for the original weights. In other words, I find the best possible tree here, and then so that'll have one leaf called W1 bar. Well, I replace that leaf by a little subtree that has two guys on it. So what have I done to change the cost? Now I've got n+1 leaves, and the cost of that tree is the cost of the other one, except that two of the paths got longer. Because they used to be, it used to be this weight W1 bar at level 5, say, but now it's W0 at level 6 and W1 at level 6. So now previously we were counting both of them up to level 5, but now they each count one more. So this is the cost of some tree, but now if I go to the optimum tree for those n+1 weights, then I can get even better cost maybe. Okay, but now look at this optimum tree for all the weights. So in that optimum tree, it's some binary tree. How does it look? I don't know, but it's got W0 is sitting somewhere, and W1 is sitting somewhere in the tree. I don't know where. But what we can do is swap these guys so that they appear at the deepest level. So if W0 wasn't at the deepest level of any leaf in the tree, let's say this was W3 here or something like that, I can swap it down and put W0 here. I get another tree, but it's better because W0 was the smallest weight of all. And so by lengthening the code for something with small weight and shortening the code for something with larger weight, I certainly can't be doing any harm. So I'm getting a better tree, or at least the same cost. Similarly, I can swap W1 over here with whoever is the sibling of this guy at the lowest level. So this means then that I can get an even better tree, or since this was optimal, I really couldn't improve it. This would be a tree for W that has W0 and W1 as siblings in the tree. So I converted this tree, which was the best for the weights, into one that's maybe even better. So it would have to be no better because it was best anyway. I do know that 0 and 1 are now brothers or sisters or whatever whatever gender you prefer for them. Now, but the cost of this tree is equal to. But now you see this is a W0 plus W1 plus the cost of some tree for W bar. Because this tree I might as well. These two guys are partners, so now I can say, well, prune them off, and I've got n weights, and I've got some tree for those n weights, the W bars, and this is greater than or equal to the best possible tree for the W bars, so the optimum for W bar. And so I started out with, and I got something greater than or equal to itself, so it has to be equals all the way down the line. So this proves the connection between optimum trees for these n weights and the optimum trees for the n plus 1 weights, and that's why Huffman's algorithm works. Okay, so Huffman did this, as I said, in the early 50s. Now, at the end of the 50s, Gilbert and Moore at Bell Labs raised the question of alphabetic codes, and wrote a very interesting paper there. But they didn't have a particularly good way to find an optimum code. It looked like, because there's the total number of trees with n given leaves grows something like 4 to the n. So you have to do trial and error. But they gave heuristic methods, methods that would be guaranteed to get within 2 of the entropy, it was a very nice paper, but it was open how to find the optimum alphabetic code, so another professor at UCSD, T.C. Hu, let's see, I'm not sure. I think he was working at IBM in the early 60s. Anyway, he came up in about 1961 or so with a method that he couldn't prove, but it seemed to work, where in every case he tried. He was able to get the optimum alphabetic code, and he kept looking at it. TC is a guy with a great combinatorial intuition. He can somehow psych out things. He discovered quite a few interesting algorithms for scheduling and things like that in those days, and wrote books on integer programming. But he couldn't figure out any way to prove that this method was working. He just sort of, felt in his bones that it was correct, but that wasn't good enough. Almost 10 years went by, and he continued to work on it. And together with one of his students, Alan Tucker, they found a proof about 1970, and this was the famous, at one time, Hu-Tucker algorithm. And in the first edition of my book on sorting and searching, this is the one that came out in 1973. I presented the Hu-Tucker algorithm, but I couldn't really give it in detail. I had to give it indirectly, and I gave it an example of the construction and so on. And then I'll read you this part here. It says, "It is beyond the scope of this book to give a proof that the Hu-Tucker algorithm is valid. No simple proof is known. It's quite possible that no simple proof will ever be found." That turned out to be false. There was a fairly, the proof was cut down to about 5 or 10 pages in 1977. But anyway, I tried to, anyway, it's a very complicated method, and almost miraculous that it worked. And in this, in the next page, I tried to present an idea to prove that the implementation could be done in order n log n time, which was actually a new result at the time my book came out. But anyway, that was the way it stood. In the new edition of my book, which makes a marvelous Christmas present, this is one of the sections that I rewrote completely. So now we have the Garcia-Wachs algorithm, and this, as I say, was Michelle Wax's thesis. She was a student of Adriano in 76, 77. It just occurred to me today while I was swimming that I spent the whole summer of 1977 with T.C. Hu, and we were visiting China, and we never talked about this particular problem at that time, but it was all going on at now the Garcia-Wachs algorithm is similar to the Hu and Tucker algorithm, but it's got a new insight, a new approach that made the whole thing start to get simpler. Still, the proof that Garcia and Wax gave would have been beyond the scope of my book, anyway, here it is in the new book. You see now what used to be called the Knuth-Tucker algorithm is now called the Garcia-Wachs algorithm. This star here means beware. It's not going to be real easy, but anyway, it's important. But the great thing, however, was that Jeffrey Kingston, about 10 years ago, so another 10 years went by, and then Jeffrey Kingston found a beautifully short way to prove the Garcia-Wachs algorithm. That's what I'm going to present to you today, and a few more ideas. I won't give the whole proof because it's hard for me to prove something in front of the audience, but I'm going to give you the idea of the proof, and so that I think you'll be able to follow it if you do buy this book. Now, however, I have to warn you that as I was preparing this lecture, I noticed a few typographic errors. Although this is really the third printing of the book, which the first printing was in April and the third printing was in August of this year, you'll have to wait for the fourth printing to get this particular page correct, because I just made the change today. But there's online errata that you can get off of the web, and if you look for page 447 on the errata, you'll see that I have, for example, here's a few little things where you change plus signs to minus signs in my proof. I don't know what, I was doing something with Emacs at the time, and I copied the. I made a mistake with the editing. And then on the next page I got another couple of typos because I was changing notation in midstream and changing my notes. Kingston's paper went left to right and mine went right to left, and so on and so on. I'm sorry about that, but anyway, a book like this, when I'm the one who finds the errors, it means two things. First of all, nobody's reading this page, and secondly, I don't have to pay anybody for finding the bug. I do like it better when somebody else finds the mistake, but I don't like to make mistakes. Still, this was fairly hairy stuff. Now. Let's see, how are we doing here? I got to try to gauge the first, when you retire, can you move? You're in front of the clock. Yeah, the first thing that goes is your sense of timing, so when you retire. So, okay, well, now, I think what I'll do is first tell you how this method, how the algorithm works, because, so you can see it's still a little bit miraculous. And then I will, show you something. Another thing you can download from the web, by the way, is a program for the Garcia-Wachs algorithm. If you look at my home page, and one of the things you can click on is downloadable programs, and on the page of downloadable programs, one of the it gives this Garcia-Wachs algorithm. This is a two-page program. This is the whole thing, just these 2 pages that does it all. This is exact. In fact. I have to admit that sometimes I write programs without many comments. This was exactly the program that I wrote when I was writing this part of the book and preparing the illustrations in that book. So if there's anything wrong with this program, there's probably something wrong with those illustrations too. But now, maybe if you haven't seen CWeb programs before, the idea of CWeb is that the program appears in small segments, and each segment tells you to read in other segments. For example, here's the main program, and the main program says declare a few registers, and then say scan the command line 2, which means section 2 will tell you what scan the command line means. And then it says do phase 1, do phase 2, do phase 3, and then you can find out what that is. So scan the command line is this thing here, which looks and sees if you give a usage message if it doesn't have a decent command line and stuff like that, and then it reads out. In this case, I define the program so that it just takes the weights W0 up to WN, and you just put them on the command line, and it tells you to have. Then do phase one is this little piece of code here, which it prints out saying I'm doing phase one, and then it does a little loop here, which calls a combined subroutine. The combined subroutine is the guts of the algorithm. I'll talk mostly about that. Do phase two. This is this really short program here. Can you read that? Yeah. So it just call a subroutine, a recursive subroutine, and the recursive subroutine is this long. So phase two is trivial. Phase three is also pretty trivial. It calls another subroutine, and so anyway, that's the whole program. But the Garcia-Wachs algorithm is a three-phase algorithm that did I say it was a two-page program? It's a three-page program. And if you want to experiment with it yourself, you can get this code and play with it. While I think about it, the last talk I gave at the end of October, I was talking about bubble sort at random, and I proved the theorem that said that if you choose by a random method to construct a primitive sorting network, 4n squared steps is an upper bound on the amount of time that you need to get a sorting method. Right after that lecture, I decided to try and find out what was the best possible constant. I proved an upper bound of 4n squared. But the natural question is, how long do you have to keep going until you get a sorting network, not necessarily bubble sort? And the answer is almost certainly 2n squared. I mean, I computed lots and lots of cases with lots and lots of random numbers, and the constant came out to like 1.997 plus or minus, something. So I wouldn't want it to be anything but 2 if it's that close to 2. So that's unsolved problem, but kind of a fascinating conjecture, I think, to how long would it take to generate a sorting method at random, and that's another program you can download is to do that kind of experiment, to do the empirical studies on sorting networks. Okay, now to the Garcia-Wachs algorithm. What we do is in this method, we take the weights and we write them down, and in this case they aren't necessarily in increasing order, and if they were increasing order it would be easy. And we put infinity before and after the weights, and now we find the smallest index k with wk minus 1 less than or equal wk plus 1. So we're looking at things that are 2 apart in the list, and we try to find the first time when we get a less than or equal. We're bound to get a less than or equal sooner or later because this infinity is sticking in here. So wn minus 1 is less than or equal to infinity. So there will be some k, but that has this property, like k equals n is going to work, even if n is 0. But keep going. Try to find the smallest k, the first time this occurs, and then we combine wk minus 1 plus wk, so add the two numbers together, and move left until you find a place where wj minus 1 is greater than or equal this new weight here, wk plus 1, and that is it is what? That's a k plus 1. No, it's k minus 1. This is a k minus 1 and a k. Yeah, k plus 1 just sits out there. It might be infinity. In fact, I wouldn't want to add to infinity. But this is so I got to move it left until it bumps against something that's bigger than or equal. So this has to be bigger than wj plus 1, and so on up to wk minus 2. Anything between the place where I stopped, I have to. In other words, after I add these two guys together, I have to shift them to the left if they're bigger than the guy to their left. I have to shift it, and so let me show you an example, and I will show you on this particular run here of the program where I started out with 10 weights, 100, 1, 1,000. I used all powers of 10 in here so that the addition isn't going to be a hang-up. We can add. You know, these are 10 different powers of 10, and so they're going to add up to 1, 1, 1, 1, 1, 1, 1. Okay, so we start out. In fact, so we imagine infinity before and after the whole business. So infinity, and then since I'm looking for the smallest k, I don't even have to input the whole array first. I keep trying. So I look at things that are 2 apart, and as long as I got a greater than relation, I keep going. So 100, you know, infinity is greater than 1. So then the next thing is 1,000. Oops. 100 is not greater than 1,000, and so at this point I have to combine these 2 guys. So I combine them, and that's it. No problem here because there's no reason to slide left. So here's what my program types out. It says I've created node 9, which is 101. It's the sum of these 2 guys as a sum of node 0 and node 1. You know, this was node 0, 1, 2 up to node 9. Node 8 maybe, huh? What is it? This is 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I've got 8. I've got 9 nodes, but they're numbered 0 to 8. Okay, so node 9 has a weight of 101, and it's the sum of those 2 weights, and so now there it is. Now, and 1,000. I didn't really put 1,000 in the buffer until I knew it would be okay. So then the next time the next guy coming in is 10,000. Again, it's going to cause some combination, and so it's another trivial combination. We add the 101. There's a 10,000 sitting out here, which I guess I can put out there in parentheses. Now I combine these 2, and I get 1,101, and then we add the 10,000. It'll get down here now. What comes after 10,000? Oh, a million. This is a huge guy. So same deal. And that gets combined in there, and then we get a million sitting out here. Now we can watch the computer. So next thing comes down is 10, and that's good because it's still less. See, this guy is bigger than this guy, and infinity is bigger than this guy, and this guy is bigger than this guy. But then the next one is going to cause another combination. The next one I guess I should have printed out here, but it's big. It's a kind of a big one. So it causes this combination. Now we're going to have to do some kind of a shift left. One of these times is going to be a little more interesting. So node 15. Let's see what's happening here. So I add this and this together. Maybe if I'll tell you what I'll do. I'm going to write just the logarithm of these numbers, or just the number of digits. 4, 5, 9, 2, 6, 8, 7. This happens to be related to the expansion of pi. Now, just a pure coincidence. So we put infinity here, but now what's happening is on this case, instead of adding the numbers together, we're just taking the max. Because when I add together 2 powers of 10, then the only thing that matters as far as the size of these numbers is to take the max. So I'll take the max. So 3 is less than 4. That's going to cause the 3 and 1 to combine into the max of 3 and 1, which is a 3. The 4 and the 5. The 3 is less than the 5, so it's going to combine the 3 and the 4 together into a 4. The 4 and the 9 is going to cause this to combine into a 5. So lots of combination going on here. Now I got infinity, 5, 9, 2, 9, 6, 2, 8. So the 8 is going to cause the 6 and 2 to combine into a 6. But the 6 is supported by a 9 on the left, so I don't have to bring the 6 to the left. So at this point I'm sitting here with infinity, 5, 9, 6, 8, and I haven't looked yet at the rest of the guys, which is 7 infinity. So the 7 is going to cause the 8 again, the 8 is supported by the 9. And the 8 is bigger than infinity, so that's going to cause the 7 to So in fact, this isn't ever getting into the next part of the loop. So the infinity causes this to combine into an 8, and then the 8, then it causes the 9 and 8 to combine. Aha! Now it gives me a 9. At this point, the 9 doesn't get inserted after the 5, but it gets inserted before the 5, because my rule is after you add the two together, then you have to shift it to the left if necessary, if the guy to your left was smaller than you. All right, that's the Garcia-Wachs algorithm, the phase 1, I illustrate it on real data on the next page. Well, actually, at the bottom of this page here, the real data. I'm taking data from English, where I'm using a 27-letter code with space and 26 letters of the alphabet. So first of all, this 186, that's the frequency of spaces, and then 64 is for the space, is for the letter A, for letter B, and finally the letter Z has a relative frequency of 1, and these numbers all add up to 1,000 in this case. So the question would be to find the best possible code for the alphabetic prefix code for English text, only using uppercase letters, say. And in this case, as we read through, you see 186 is bigger than 13, 64 is bigger than 22, but 13 is less than 32. So this 32 is going to cause us to add 13 plus 22 together, and we should combine these and get 35. Let's see if the computer actually did that. It comes in here and says, "Yep, 13 plus 22 is 35." Okay, next, this 103, 35 is less than 103, so that's going to cause the 32 and 35 to combine into 67. But now that's going to have to shift to the left of the 64, because 67 is bigger than 64. Here we get to so this 67 actually has to slide in here to the left of the 64, and that's the state that you see at this point here, where it's 186, 67, 64. 103 is coming up next. Wait, where did the 103 go? What?
But don't you break the lexicographical order when you are making shapes?
Don't I break my lexicographic order? Yes. This is exactly why it's an amazing algorithm. And we're going to have to do this. Yeah, I'm glad you noticed that, because this is the whole reason why nobody believed TC for so many years. Yeah, because I've got a different problem. I moved the 67 out, yeah. But I'm just trying to figure out what happened to 103. Excuse me.
67 is less than 103.
Oh, now it combines again. So the 103 is still sitting out there, and 7 combines with the 64, yeah. But it's at the left of 64, no, it's not at the right of 64. That's actually going to be somewhat important. And then the 103 comes out here, and we keep on going, okay? Now the whole process is shown here in this chart. So you see the 13 and 22. Can you zoom in? Give the close-up. Yeah. So the 13 and 22 combined to make this 35 here. Then the 32 makes 67, but that shifts over with the 64 and combines into 131 and so on. Makes this rather hairy combination. But the fact is that even though we are sliding these things around and destroying the alphabetic order, we're getting a problem that turns out to be equivalent, in a proper sense of equivalent, to the original problem. And that's the weirdest thing. So we get this tree, and finally we reduce the thing down until we got only one weight left. And one of the exercises in this book says, well, what happens if you untwisted everything and opened it up into a binary tree, and said, well, what order would the leaves appear in this thing? And if you look at the answer to that exercise, it tells you the order in which the things appear. Of course, you're not supposed to look at the answers, unless you're the author. Now, here it is. This is the order. Actually, the space occurs at the end instead of the beginning. and the letter E comes first. Now let me explain that. What's the first leftmost thing in the tree? Well, you follow all the left branches. So you go left here, and 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 you get to the letter E. And what's the rightmost character? Well, you go right, and it takes you to the right, and you're down here at the space. So after you untwist this whole thing, you get a weird binary tree. However, the thing about this binary tree is that it's going to turn out that it has the same cost as the best possible alphabetic code. So the binary tree that you get turns out you can to be a tree that it has all kind of branching, goes to the left and goes to the left, and all of a sudden has an E here, and goes to the right a few times, let me see. Actually, at the second level, the space occurs, and the E occurs at the 1, 2, 3, 4, 5th level. 1, 2, 3, 4, 4th level. 0, 1, 2, 3, 4. So the E should actually be here. But you can expand that whole tree out, and you can figure out the level of every leaf in the tree. And so you get a pattern of level numbers. As I said, like the space was at level 2. Now you sort the leaves and you keep their levels, and you say, well, space is at level 2, A is at level 4, B is at level 6, C is at level 6, D is at level 5, E is at level 4, as I said, F turned out to be at level 6, and so on. Z turned out to be at level 7. X and Y were at level 8. And now you look only at these level numbers, and you build a binary tree that's defined by these level numbers. And that turns out to be the answer to the problem. Now, is this magic or is this math? I mean, this is why it's the same kind of thing happened in the Hu-Tucker algorithm. You started out and you started moving these nodes around and destroying alphabetic order, and then all of a sudden at the end it says, okay, now you've got a binary tree that gives you level numbers. Now use those level numbers, and the level numbers from that binary tree are the ones you finally use. And as I say, they finally found a long proof that showed that it was true, and Kingston found a short proof. So this is the winning code for the alphabetic frequency data, and if we convert that to actually zeros and ones, here's what it says: make a space come out as 00, and the letter E has four bits to it, and so on. And the average number of bits per letter, according to this, is 4.2. Well, 27 letters. You could do it with 5-bit code, just because there's 30. You could get 32 letters in a 5-bit code. With 4.2, you're saving about 15%. It's not too bad. In fact, it's optimum. It's the best you can possibly do for alphabetic coding. Now, how can anybody prove that such and such a method works? And the thing that Kingston started out with was a very nice, beautiful, simple observation that leads to that makes the problem start to simplify. And his main idea is, suppose you have a case where WK minus 1 is greater than WK plus 1, as in our example. He says, if this holds, then in the optimum tree, in any optimum tree, level of K is less than or equal level of K plus 1. In other words, if you got a large weight and then followed step 2 by a small weight, then then the guy in the middle is actually going to be up higher in the tree or at the same level as the small guy is. So I mean, a small weight usually corresponds to a large level. So this is the first theorem. And furthermore, if they're equal, then in some optimum tree, not all of them, this inequality holds. Now, this is every optimum, and this is some. So now, how do we prove that? And that's that's a key to the thing. So let's suppose that it's false. So suppose that I have a case where I have an optimum. I have a tree, let's say, that that doesn't have LK less than or equal LK plus 1. So suppose we have a tree with LK greater than LK plus 1. So that means that there's that leaf number K is sitting here, but it's at a higher level than K plus 1. K plus 1 might be 1 level higher, might be 2 levels, 3 levels, 5 levels higher, but it's not. It's definitely in this direction. And remember that I've got this relationship, one of these two relationships on the weights here. Now, if this is true, then that means that this leaf K has to be the right child of its family. There is, it's certainly not going to be a left child, because then K plus 1 would be down here somewhere. K plus 1 would either be the brother sister, or it would be nephew niece or something. So we got. So I know that it's the left child, and then it has a sibling, which either is a leaf or maybe goes below. But there's some weight here, which is the sum of all the leaf's weights here, and K minus 1 is sitting here. Either K minus 1 is sitting here, or it's somewhere in this subtree. So I know that W is bigger than or equal W to the weight of leaf K minus 1. Whatever the weight is that's on this half of the equation, there's some tree here. It might be just one leaf, but anyway, it has a total weight exceeding that. And I have to say that the weights are assumed to be non-negative. Huffman's algorithm works with negative weights, but this alphabetic code, I think it's open problem what to do with negative. No, I think somebody did figure that one out, but this algorithm applies only to very definitely to non-negative weights. So the reason I can get this inequality is say that it's either the weight of W is either equal to WK plus 1 or some other weights added onto that. So it's got to be more. Okay, so here's the idea. Now we take this tree and we form a new tree that moves W up one level and moves K plus 1 down a level and joins it to K. This is another tree which has the same leaves in the same order, so I can see what happens. So this is the old tree. This is the new tree. The new cost is equal to the old cost minus W, because everything in W shifted up one. And then plus WK plus 1 because this leaf shifted down plus 1. And then it also might minus something. Depending if K plus 1 is actually just one level higher, then K stayed on the same level where it was. But if K plus 1 was sitting up 2 levels higher, then K has moved up, and we've saved the new cost is even less than before. So it's less than or equal to this. But W is bigger than WK minus 1, so minus W is less than or equal minus WK minus 1, which is less than or equal to W minus WK plus 1. So this is equal to this is less than or equal to the old cost. So the new cost is less than or equal to the old cost. That means then that if I started with an optimum tree, in fact, it would be if I started with the strict inequality here, it would be strictly less than. This would be a strict less at this point, and so I couldn't have had an optimum tree. This couldn't have been an optimum tree because I got a better tree in the case of strict inequality. But if I had equals sign here. So these two are equal. Then I have found a tree in which these guys are at the same level, and so there exists some optimum tree with LK less than or equal LK plus 1. Either it was less than or it was equal to. It could have been less than because I started out assuming not less than. But, okay, so that's the initial problem that makes that starts to crack this program open. And now we start to explore it by considering. Remember when I got these infinities here in the W2? Suppose that I'm building up a sequence of weights in which W0 is bigger than W2 is bigger than W4. You know, these things bigger than W6. W1 is bigger than W3, bigger than W5, but now maybe it's less than or equal to W7. Here's where the collapsing rule starts to take place in the Garcia-Wachs algorithm. In this case, we would start adding together W5 and W6. So suppose we have a situation like this. Now, look at what our lemma tells us. Since W0 is greater than W2, the lemma tells us that level 1 has to be less than or equal level 2, because that was the, take k equals 1 here. Okay, now W1 is greater than W3, so now we take k equals 2 and says level 2 is less than or equal to level 3. And so this keeps on going, and so we get a nice monotone condition here on our levels until level 6, because W4 is greater than W6. Now W5 is less than or equal to W7. Now I'm going to use this lemma in reverse. And so let's write down the reflection of this lemma. If WK plus 1 is less than WK plus 1, then in all optimum trees, LK is less than or equal LK minus 1. And just flip left and right in the whole thing. If equals holds here, then there is some optimum tree in which the same thing holds, LK less than or equal LK minus 1. And so the conclusion is that this holds in all optimum trees, and L6 is less than or equal L5. Let's write them all in here. L6 is less than or equal in some optimum tree because of the left-right reflection of that lemma. Therefore, L5 equals L6 in some optimum tree. Okay. So I've got these two nodes that I was going to add together. I've got them at the same level at least. Okay. This is the way you start getting insight into the problem. And although I don't have time to go into it, the book has almost correct explanations, which show you how you get further structure by going to the left. It's saying if this sum is bigger than the guy to the left, then we keep looking for a place where we slide to the left, and that gives you the next lemma here, which gives us further structure, which tells us about sliding to the left, and you just change the plus signs to minus signs, and you got a good proof. And then what turns out is that something that you can see at the bottom of the page here. I take my two leaves that we were going to add together, and I move them and I move them off to the left, insert them between j minus 1 and j where they fit according to the ordering, and I now got a problem on one less weight because if I add together these two weights, I got a problem on one less weight. Which see this Q, I'm using Q instead of W right here, but it's you add together those two weights, and you get a problem that has only n leaves instead of n plus 1 leaves, and you solve that problem. And now you show that every solution to that problem also corresponds to a solution to the original problem on which these nodes you put would appear at the same level in another tree. So basically, the solution to this, all solutions to this problem, in this order, correspond to solutions to trees that have the optimum cost in the original problem. And after you find the tree, you can slide. There's a way to keep leaves on the same level and get a code that has the leaves in the correct order. And that's the solution to this thing that seems incredibly impossible, but is actually works, and the proof is there. Now, I have just a few minutes left, and I wanted to show you some computing I did this morning with this, or this afternoon actually, with this program, because it's not really known much about the running time of the thing. Now it turns out that the particular algorithm that I've got for downloading is order n squared. It's possible that see, as you're adding things together and moving them to the left, you've got to slide. You've got to slide some numbers. Let me I got some bunch of numbers like this, and I add these two together, and I stick them over here. And I'm implementing this in sequential memory. I actually haven't. And after you stick it in here, you have to also check again. This might cause ripple effect that you have to add. That you'll have to combine some of these guys and move. And keep on moving down. It doesn't. It's not just stopping. You still have to have this condition of the thing being sorted by twos afterwards. So as I move this over, I'm shifting these guys one space to the left, and I'm shifting these guys one space to the right in order to make room for the new guy. So I'm doing a potentially order n moves each time I do this, and I repeat this order n times, and it can actually go as order n squared. You can concoct examples where it'll take that amount of time. But exercise, there's of course using better data structures, you can do it. The best solution I know is to keep, however, it's fairly complicated. You need to keep a balanced tree together with doubly linked list of all the leaves. But that's enough to implement this in the guaranteed log n time. But still, there's all kinds of algorithms out there where people do overkill in order to guarantee the worst case. I mean, they make the program so complicated that they're paying a terrific overhead penalty in order to guarantee that they're going to get good running time. And in fact, it might turn out that it's very rare that you ever have to move very many guys to the left or very many guys to the right. It's only in the worst case that this happens. In fact, a couple of years ago, I talked about a problem about optimum rounding, and which is reduced to a network flow problem. And you use the fancy algorithms for network flow, and they were running a lot slower than the brute force algorithm. That wouldn't have any good guarantee at all. So I was wondering about this algorithm. What actually happens on it? So I took one model of the problem which looked like my decimal one that's based on pi, but I'm using binary numbers, and so imagine that the leaves of the tree are all powers of 2, all distinct powers of 2, but they appear in a random permutation. That's one model of saying a random data, but this means the weights are pretty spread out. It's equivalent to taking this algorithm and using the operation of max instead of plus, as we saw. And so it's interesting to say how many times are you going to be sliding things to the left, sliding things to the right, and so I tried it out on, for example, running n equals 100, and this is just my random number seed, so this number you don't. And so I did 10 runs on random numbers, or random permutations of 100 elements. And how many times do I slide something downward and how many times do I slide things up? And so it was pretty much about 13.5 downward per thing, and 1.6 or 16 and 0.2 typically on the coming up. So if I did 1,000, I was getting where's the total? Didn't get in there. Well, anyway, you can see it's all coming about the same. Here it's 10,000. It's here. You see, I didn't generate this by computer, but I did it by text editor. But I took it out of the shell script, out of the shell window. But anyway, I didn't want to show you my typos. Notice what's happening here. It looks like it's converging. In fact, here I'm doing a million items and taking 10 random permutations of a million items, and very close to saying that this is about 1.4. We're very close to 1.4 or 1.39. 1.39 times the number of items, 1.38. It seems to be converging to some constant, whatever that is. But it's growing linearly, the amount of motion. So the algorithm on this model, where you take random permutations of powers of 2 as your weights, it's definitely somebody's got to be able to prove that this is linear. In fact, look at this constant. 1.66667 times the number of items. If that isn't 5/3, I don't know what is. So this has to be, it has to be true that you're doing 5/3. I don't know what this constant is, but but there it is. Maybe Euler's constant plus something. I don't know. But anyway, this is really suggestive that the amount of time you slide something up during this process. And the algorithm is just the one that I described, except that instead of taking the sum, you take the maximum, and then you shift it to the left where you have to. And you count how much you shifted things to the left and right, and this is the number that I'm giving here. Then I tried another model where I took random fractions between 0 and 1 on the leaves, and here I haven't had a chance to look at it yet, but at the data, but. It seems like it's going like n squared, because here you see I went from 100 items to 1,000 items, and the number of motion seems to have gone up by about 100. So I went up by a factor of 10, and this is not quite 100. This is about 86, and then here it's not 100. It's more like a factor of 50. And this went up by about 100. This is not going up by that much, though. So 70. So, and this is so I haven't. But these numbers are pretty stable here. They might depend on. They probably depend something on the actual way that this number breaks down as a sum of powers of 2. Because what happens is when you have this sort of waves appear at different logarithm levels when you're adding numbers together. And things start to group around a certain, the ones that are a sum of 5 quantities tend to group, and next to the ones that are a sum of 6 quantities, and so on. So there's probably something to do with it. I haven't any explanation for this, but it definitely looks like it's going, if not n squared, n to some high power or something or other. Here's a case where I took the weights, instead of being random fractions between 0 and 1, I took random fractions between 1 and 2. And you get different statistics. Nothing moves down in the small case, but I was getting again something like this, but not quite n squared behavior. Oh wait, this went up by a factor of 200. Yeah, it's very inexplicable, but looks like. Depending on the kind of weights that you're working on in this, you would want to use a more efficient algorithm than if you had a large problem for a large code. It would be good to use a better data structure than pure sequential. You would use a large code like this if you were, for example, making a code for English, but not only for one letter at a time, but you would take, say, groups of 3 letters or something like that. And then find the best alphabetic code, or variable size groups, making a variable code. Anyway, there's lots of different alphabetic coding techniques. Okay, the biggest open problem, the most famous open problem, is to get a lower bound. Nobody has been able to prove that there doesn't exist an algorithm, a linear time algorithm for this problem. this algorithm, I say, with good data structure, you can implement it in n log n time, but nobody has been able to think of a way to show that it's got to take n log, that somebody might not next week invent a linear time algorithm to find the optimum alphabetic code. You can get the optimum Huffman code in linear time once the weights are sorted for you in advance, and that is known. If the weights aren't sorted in advance, it's not known whether or not the Huffman code algorithm can't be done in linear time. Okay, so those are the open problems I know right now. This one about the 5/3, which has to be true, which is just an interesting little algorithm that has a known average time, but no known proof why it should have that average time. And then this famous problem about what's the fastest way to get an optimum alphabetic code. Any questions? Come on, there's got to be a question. Yes.
How did the previous algorithm?
Who took our algorithm?
How did that compare to this? Was it like n squared equals n log n?
Oh yeah. So it could be done with n log n, but the constant proportionality was huge. It was really it was like it used to be a level 41 problem in my book to implement it in n log n time. In other words, a rather difficult term project for a couple of students in 144C or something like 144B. This another page of code, and I would have an implementation that would be n log n. I forgot to mention another really nice theorem, and that is, suppose you know the weights that you don't know, but you want to get an upper bound on the alphabetic code, or let's take another way. You've got a whole bunch of weights, and somebody says, move these weights around, find the hardest possible order in which to make a code for these weights. So now we're knowing only the weights, and your enemy is allowed to put those weights in any order whatsoever. What's the hardest order that he can do to make it hard for you to do it? And here's what suppose the weights were actually in increasing order. W0 is the smallest. The actual worst case to do it, I believe, is something like this. You go one like this, and then you leave gaps in here, and then you go. I'm sorry, no. W0, what W1? Wait, no. It's the order significant? In other words, for an alphabetic code, you're given the order of the leaves. So in Huffman code you're not. So if your weights are 1, 2, 3, 4, 7, 10, 11 or something like that, at Huffman, the optimum code, if you didn't have to preserve alphabetic order in the messages you're transmitting, you could make Huffman's algorithm would tell you how to combine these and get a code. But the code would preserve messages, but it wouldn't preserve order of messages. But in the alphabetic code, you're also saying the order has to be preserved, and the idea is actually you put the let's make this 13 so they're all unequal. So given these weights, what's the hardest order to achieve, to handle, and you do it this way. It's 1, 13, 2, 11, 3. In other words, you write 1, 2, 3, 4, and then you put the 13, 11, 10, 7 in that order. So it's this kind of a mixed up order where you take the smallest and then the largest, and the second smallest, second largest, and keep on going like that. And now you say, apply the Garcia-Wachs algorithm. And the Garcia-Wachs algorithm works a very neat way on this. It adds 1 to 13 and makes 14, and it adds 2 and 11, and it adds 3, and it adds these guys. And so it turns out you're adding together the largest and smallest, the second largest, second smallest, and so on. And then it turns out to be equivalent to Huffman's algorithm after that point. And so this is a theorem of Kleitman and Sachs, Danny Kleitman and Mike Sachs proved that that of all the arrangements of it, this one has the worst possible final coding length, final optimum coding length, and you can get it by adding together the extreme guys like this and then applying Huffman's algorithm. Because in this particular style of ordering, you can show that Garcia-Wachs algorithm emulates Huffman's algorithm. Craig?
So you can think of arithmetic codes as kind of a fancy version of Huffman codes. Is there an equivalent fancy version?
No, arithmetic is worse than Huffman code by a little bit, by a constant factor.
So is there an equivalent fancy version of these alphabetic codes?
It's what?
Is there an equivalent?
Yes, that's theorem. That's theorem M. No, you got to buy this book. So it's theorem M on page 445, which might have a, nobody's read this page yet, so you might be able to recoup the cost of buying the book if you find it. But there's a very nice little analog of the arithmetic coding that applies to this case. In fact, no, I'm sorry. Theorem M is even more general than what you asked. The original case was actually solved by Gilbert and Moore. The arithmetic coding for alphabetic case was solved by Gilbert and Moore, who Shannon himself came up with the arithmetic code for the unordered case. That's all in here anyway. Yes.
As long as the ratio of the weights stay the same, then you get the same code, right?
Yeah.
So then, if like that range between 1 and 2 and 0 and 1.
That's not true. You see, if you suppose you add a constant to every leaf. So every leaf now has weights m plus W0, m plus W1, m plus, and so on. Okay. Now what's happening is that you're adding to you're adding m times the length to the whole thing. So as m goes to infinity, the optimum tree is going to be something where everything appears at log n level. Yes. Incidentally, I tried the case where all the weights are constant, and there it was going as there it was actually there were no downs and the ups was very small. The algorithm is very good in that case. It's just these little twiddles caused by the randomness caused the shifting around. But when in case of equalities, the things would sit there and be very nice.
So alphabetic codes and binary search trees, they come in a lot of applications. But two things that we worry about in real life applications is that we do not care about the absolute optimal so much, but within some factor of the optimal. And second, of the worst case length of each leaf, the height of each leaf is limited to a bound.
Yeah. Okay. So there are other algorithms that get a little bit more complicated, but still can be based on this theory that give you that give you things with bounded level, and those are discussed in exercises here. But I didn't go into that. Now but when you say that you're only concerned about getting within a close, it's small amount of the optimum, I think that's just tradition. I mean, really, these methods give you enough of a percentage that it can be important. I mean, some people say that it doesn't matter to throw away a factor of 2 or a factor of 20% or something. But that's not their opinion when you talk about their salary. I mean, so there are cases where people will fight for that 20%, and so I considered, for example, in here a case where the best possible theorem says that the lower bound on a code, which you could construct from the entropy, is 3.38, and the best upper bound saying there exists a code by this general scheme is 6.6. But then you actually work through the algorithm and you find out that you get a code that's 5.01. And so These algorithms are actually can actually give you a payoff if if dollars mean anything to you, and you can convert this to dollar.
Does there exist a linear time algorithm which can give me a not exactly optimal cost, but
Arithmetic coding. Well, no, I guess that isn't necessarily. That's the linear. You mean for alpha? Yeah, I'm not. I have to think about that. I mean, it's. I don't know if anybody's implemented. I mean, conceptually, it's very nice because you just look at the partial sums of the frequency distribution, and then you you cut off. But when you say linear time, it's not clear when you. I mean, the pre-processing, how you handle it. Yeah, there's I had a paper once on something that also Gallagher had done earlier. I didn't know about it, but it was for linear for doing Huffman coding on the fly, dynamically updating it. Like if you're trying to send files by FTP or something, you want to compress them and you want to sort of learn the statistics of the source as you go, and so you keep on updating it. And I had a method that was that was linear time, but it needed, in some cases, you were looking at the tree up from the top to down, and in other cases from the bottom up. And so when you actually started to study the hardware, it was not exactly clear what you meant by linear time. These questions are kind of tricky. Now next year, probably beginning of February, I'm going to give another talk, and I'm really excited about it right now. I'm designing a new computer, and I'm going to it's going to be the computer for the next millennium, and so I'll present it in the next talk in this series. Thanks very much, and have it.